Okay. Hi, everyone. To Angelina Ballerina learns about memory allocation. What's that for the video? One more thing. We were almost ready to start. Okay. These things get more complicated when you have hair. It's like a peril of being a female conference speaker. Okay. It's like a headband, really fancy headband. Okay. All right, is this good?
Yeah.
Okay. Okay. I am really excited to be here today talking about Angelina Ballerina and memory allocation. First, I'm going to tell you a little bit about myself. I usually don't start this way, but I discovered in putting together this talk that when you're talking about like garbage collection and memory allocation and sort of like fascinating, but these heavy technical topics, it's surprisingly really difficult to just easily weave in a little bit about yourself along the way. So I live just outside of Washington, D.C. Most people probably think that my life there is a lot of this and this and this. But I actually live just outside of D.C. in Tacoma Park, which was recently ranked the 8th most liberal town in America and is referred to as a hippie haven. It's also an official nuclear-free city. I also have a 2-year-old named Devin. You might see him running around the venue or Barcelona. He's off with his dad doing adventures today. And Devin loves talking about garbage collection. As I was preparing for this talk, every time garbage collection came up, it was really exciting. He would look around for garbage trucks. I would try to understand another complex algorithm. But it was really nice to know that we both had this shared excitement about garbage collection and what that means for each of us. I also work as a developer at Collective Idea. Collective Idea is a software consultancy based in the US. And Collective Idea is a really fun place to work because we deal with all sorts of clients. Everything from Fortune 50 companies to just small startups getting going to internal products. For a project at Collective Idea, we were working on an application that involved generating enormous Excel spreadsheets, like hundreds of rows and columns, multiple worksheets, just really gigantic. The rest of the application was pretty simple. But this spreadsheet generation was really the core of what the site needed to do. So we're chugging along, building this application, optimizing active record queries here and there as a concern for speed. And then one day, we're testing some functionality, and everything just goes bonkers. We're getting errors everywhere. Our web server usage graph has red and lots of those little colored boxes, like the ones that you really don't want to see. And this kicked off a whole team investigation into what was going on and how we could solve it. So part of solving it was through understanding it. I may have already used a bunch of terms and phrases that you might not know, and you might be thinking, oh, maybe I should just walk out of this talk if we're not even speaking the same language. And I agree with you. I've been to lots of conference talks and read blog posts before that involved words like Heap and malloc and all of these resources that just felt like incomprehensible words being thrown my way to jot down later, to maybe understand. So today, we're going to go over some definitions and scenarios, and we'll dive into each of these concepts to understand them better, and then talk about some tools that we used in order to help figure out what was going on and how to put those in place. I'm mostly going to talk about Ruby code bases. And we're going to do this through Angelina Ballerina. How many people here know who Angelina Ballerina is? Okay, a couple. Angelina Ballerina was a book that I read a lot when I was a kid. I was a ballerina back in the day. How many folks here were dancers? Any dancers? No dancers. Well, then you'll really learn a lot today. So Angelina loves to dance. And in this book, she dances all the time, day and night. Because she's so focused on dancing, she forgets to do everything else. She forgets to clean her room. She forgets to get to school on time, and so on. Her parents do not know what to do. They finally decide to enroll her in a ballet school. And once they do that, she's so focused while she's there, and she's so focused on getting back to ballet school that she's able to accomplish all of the other tasks that she needs to. And eventually, she becomes a famous ballerina. So obviously, there are a ton of parallels about memory allocation, partitioning memory, focusing, and shaping memory into structure and format that makes the program, or Angelina, as productive as possible. There are also similarities between dance and learning about memory allocation. Aspects about remembering steps, understanding what's going on, knowing the counts and what steps fit. The real goal is to walk away with a better understanding of what each of these pieces, terms, and words that I discovered through that process are, and a better understanding of the tools that you can utilize to look into memory-related components of your application effectively. And I'm going to try to help this really sink in by using actual stories related to Angelina and dance, so that they're not just words and definitions. I have a few caveats. First, I'm going to focus today on standard Ruby and some Rails because memory allocation and garbage collection are enormous topics and work slightly differently in every programming language. And second, I also want to add that there are a lot of memory or performance tweaks that can be made by looking at database queries, especially when using like Rails and Active Record. I'll mention some related tools for this, but I'm not going to dive into like the actual active record optimizations, N+1 query fixes, things like that. Okay, so let's get started. We were first alerted to this problem when we started getting web server errors. We saw request timeout errors. Request timeouts happen when an HTTP request takes longer than 30 seconds to create. So the request is still going and it may complete, but it means that the request that was sent to the Heroku router via dynos took longer than 30 seconds to complete. Heroku is the service that we were using. Then we got memory quota exceeded errors. This means that the dyno needs more memory than it has. You'll see this sort of error in your logs. So, related to Angelina Ballerina, to take the base of the story's plot, Angelina is so focused on dancing and loves to dance so much that she never remembers to do anything else that she needs to. She never takes a break and is late for school, requests timeouts, and just simply can't remember the things that she needs to. Memory quota exceeded. So her situation, like ours, leads to all sorts of errors in not being able to remember what she's supposed to be doing next and running out of time to do things. So this is what that web server graph looked like. We had a few processes running in different threads because splitting portions into threads and background jobs earlier helped solve some of our earlier performance issues. This is where you can tell sort of where those threads and those different dynos are. And we saw that we were running out of memory when these colored boxes appeared. Now, we can't get very far into understanding memory and the tools without understanding some basic terms about memory. So we'll start with some of the basics. Memory allocation is asking for a box. It's like, give me a place to start doing stuff. Memory is the actual box. This can be heap or stack. We'll get into that in a minute. Memory usage is putting stuff into the box. So how does Ruby use memory? Well, Ruby uses memory by retaining objects. There are two types of memory, stack and heap. Stack memory is memory that's temporary. It's like local variables that are created when you call a specific function. So Angelina's focused on dancing. Once she's enrolled in dance school, that's her heap. There are all sorts of things that she needs to remember while she's at dance school. We'll get into the Heap next. But the one-off tasks are like being on the stack. Clean her room, help make dinner, do a chore. She can remember these for a short period of time, do them, and then forget about it. Heap is unmanaged memory, where you're saying, please just give me this blob of memory so that whenever I call a function, there's already memory there. Malloc is mentioned in a lot of garbage collection and memory talks. Malloc is actually a function in C. It's the function that actually allocates a certain number of bytes and puts a pointer at the first byte of allocated space. There's also calloc, free, and realloc functions. Malloc basically stands for memory allocation. So Angelina in dance school uses her Heap memory. It's all of this space that's allocated for dance-specific knowledge. But whether she's learning about a turn or a new ballet position or a dance step, she's made the space in her mind to dedicate to learning and remembering all things related to dance. And within that heap, there's the Ruby heap and the machine heap. So the machine heap is like a big blob, and then the Ruby heap is the portion of that machine heap that's focused just on Ruby-related functions. So within Angelina's dance heap, there might be a small portion that's dedicated to ballet. Her overall dance memory might also contain information about tap, jazz, folk, all different kinds of dancing. So there's a heap, and within that heap, there's a chunk or page allocated. And inside that chunk is a linked list. Each node in the linked list is a slot, and each slot is a Ruby object. So the heap is ballet. The chunk are ballet feet positions. The list is a list of ballet positions, and each slot is an actual ballet position. So these are just called first position, second position, etc. So it's like each slot is one of those positions. The list is what's called a free list, which means the program looks to find the first open slot, and that becomes the Ruby object. Once the slot is filled, the pointer, which the pointer is just a thing that says like, here, look at me over here, over here. It moves to the next free space, and that's called bump pointer allocation. When all of the slots are filled, that's a full page. When there's a full page, a new page is allocated. This new page is called an Eden page because there are available slots. The objects filling up each of these slots are called retained objects. Memory usage grows in Ruby programs as more objects are retained or as more of these slots fill up. So here you see that now there are retained objects in 11 slots and new memory is allocated for what might come. So as Angelina learns more steps, more turns, more dance terms, she can't remember everything. She needs to prioritize what she remembers and what she no longer needs to. When the garbage collector runs, the allocated objects can be collected and thrown away so that you can reuse those slots. So what is garbage collection? To further understand the difference between memory usage and memory allocation, we're going to take a brief detour into garbage collection. I'm going to take a sip of water. Garbage collection is a type of automatic memory management that makes a program seem like it has infinite memory by reclaiming objects that are no longer in use. So there are languages that have automatic memory management or garbage collections and ones that don't. So for example, Ruby or Python both have automatic memory management language, are both automatic memory management languages. You don't need to think about memory and allocation of objects or implementing garbage collection in order to free up memory manually. The language does that for you. But in a language like C, for example, there's no automatic memory management. So part of what you need to do while programming is worry about asking for memory, freeing up old memory, and only accessing and reading and writing what you're allowed to. Garbage collection was written about first in 1960 by John McCarthy in his paper, Recursive Functions of Symbolic Expression and Their Computations by Machine, Part 1. The best part about this paper is that there is no Part 2, there's only Part 1. So this paper talks about Lisp and some of the interesting aspects of Lisp. One of those things discussed is this idea that the program automatically is able to allocate and free memory. This idea developed into what we call garbage collection today. We talked about some garbage collection related words before when I was going through just the basics of how memory works, but I'm going to mention them again through this explanation because it's a lot of words and concepts to sort of soak in. You might be able to understand them in a different way looking at the definitions through the lens of the garbage collection process. So garbage collection has two parts, the allocation and the collection. Think of the allocation as the steps to perform the dance, and the collection is the person that's actually doing the dance. The allocation refers to the heap or stack. Remember, the heap is a data structure that you have access to, and you can allocate and deallocate objects from the heap. Additionally, as opposed to stack memory, this allocation and deallocation can happen in any order. A heap can be an object graph, which is a directed graph where the nodes are heap objects and the directed edges are references to the heap objects in the slots. We're definitely going to break this down further. So here, like the root is Angelina, the nodes are the positions or turns, and the references are the choreography that get you from one node to the next. The stack are specific allocations based on methods or functions that are called. So stack allocation focuses on last in, first out. Allocation onto the stack where the record, let's say Angelina cleaning her room, is pushed onto the stack system when the process is called and then gets popped off once the process returns. Garbage collectors have three main responsibilities. They allocate memory for new objects, they identify which objects are garbage and are no longer being used, and finally, they reclaim that memory by freeing those no longer used objects. So talking about the heap, looking at allocation and identification, that's part of the allocation piece of garbage collection, the steps of the dance, whereas the collect part is obviously related to the collection, and doing the dance and forgetting about the moves as we finish them. So some of this may sound familiar. A granule is the smallest unit of allocation that exists, like the idea that there are positions in dance. A chunk is a large group of granules, like an allocation chunk. A chunk are all of the ballet positions that exist. Chunks have lists, and these lists are linked lists of nodes. This is like the list of ballet positions, and each specific position is a node. Each slot is an object. Each node on the list is a slot, and each slot has an R value, which gives you information about the node. An R value is the R object and the R string and the R class. And this slide is stolen. Pat Shaughnessy did a garbage collection talk a couple of years ago, and this is like the best diagram that I've found that explains this. This is directly stolen from his deck. So each node or slot is like a ballet position, and it has a value, which is the object, string, and class. So this would be something like the string first position, let's say the class of position, and the object, which is position1 equals position.new. This slot also has a reference or pointer. Remember we talked about the bump pointer before, and an address. Objects on a heap are talked about by using their address, and objects can refer to each other. And these slots are pages which are contiguous on the heap, which basically means that they're together on the heap. The total number of pages that a program needs to keep in memory to avoid increasing how long it takes a program to run by more than a specific percentage is the program footprint. So a program, in this case like a choreographed dance, the dance has a lot of different steps and turns, and you also need to know a lot of ballet fundamentals like the positions and other information. All of the information that you need to know about this particular dance is the dance's footprint. These pages and slots are also referred to as the object space. In conjunction with this idea of allocation and collection, garbage collectors have a mutator and a collector. The mutator is the code that produces the garbage. So, like if there was infinite memory, then the collector would be great because there would never be any garbage that actually needs to be collected. But That's not our scenario. That's not what actually happens. Our programs fill up memory and create objects when it executes. It mutates the heap. So think of the mutator as the dance steps. Let's say you do a certain type of turn at the beginning, and then you never do that turn again for the rest of the dance. The dance and the turn are part of the mutator, and then it can be forgotten about and collected by the collector. So now we'll look at the collection portion. The collector first identifies which pieces of garbage are ready to be taken out by tracing through the edges or references from the root, and anything that it doesn't connect to is garbage. It does this by looking at the references from the root. Roots are areas of the heap that can be reached without asking other areas of the heap how to reach them. They're entry points into the heap. So in Ruby, for example, the object class is a root object in the heap. The collector finds the unmarked nodes and sweeps them away in one type of garbage collection algorithm. The collector is triggered based on thresholds, and thresholds are the number of slots. So once we're out of slots and we need more, garbage collection is triggered. There are a few different garbage collection algorithms or approaches. I'll briefly go into 4 of them, and then we'll really drill down into Ruby's garbage collector. The 4 approaches are copying, mark and compact, reference counting, and mark and sweep. So first is reference counting. Reference counting means that every time you refer to an area of memory in the heap, you keep track of how many times you've referred to it, so you're keeping count. An object is only live if the number of references to it is greater than 0. So you can easily say, okay, great, all of these allocations are 0. That means they're garbage and can be collected. The biggest problem with reference counting is that if you have 2 objects that refer to each other, the reference count will always be greater than 0, and so there'll never be garbage collected ever. It's good, reference counting is good because it's incremental. You don't need to stop everything to figure out what's going on and trace through the whole graph. But it's bad because there's a lot of overhead to constantly counting and keeping a reference. In real life, deferred reference counting is usually used, which can lead to floating garbage, still require application pauses, etc. Objective-C and Python use some sort of reference counting garbage collection. So next, copying. The copying collector reduces the size of the available heap. It divides the heap into 2 semi-spaces, the from space and the to space. The objects fill up the from space. Once you've figured out which are the live objects and which are the garbage objects, the live objects are copied from the from space to the to space. And whereas in the from space, all the garbage objects were interspersed in the heap semi-space, when they're copied over, they're all put together and compacted, and the pointer moves to the end of the live objects, demonstrating where more allocations can be made. Then the from space and the to space are swapped. So the from space is where the live objects are, and the to space is ready to be copied into again when needed. The biggest issue that you see with the copying collector is memory fragmentation. You could have a from space that looks like this. And you have places to put memory, so it doesn't seem like we need to do any copying yet. But none are actually big enough for the object that we need to place. So finally, mark and sweep. There are 2 variations, regular mark and sweep, and mark, sweep, and compact. In this type of garbage collection, the collector goes through all of the objects and marks everything that's still live or where there are still related pointers. Then it sweeps, and for mark, sweep, and compact, it rearranges the heap and compacts the objects. For just mark and sweep, again, it's the same steps except without the compacting at the end. So here, when the slots or nodes of the linked list are used up, then in Ruby, stop the world marking happens. Our entire application pauses and goes through all of the references and marks anything that's live, which means there's still reference from the root node. Everything else is deemed as garbage. The whole object graph is traversed in order to do this. So this type of stop the world collection happens in a lot of garbage collection approaches. So our linked list nodes are each of the nodes here. Once they're all filled, we stop the world while we go through that whole tree. We see the root is Angelina, and everything that's referenced from the root is ballet. But these 3 nodes are related to other forms of dance. They're no longer referenced by the root, and so they're garbage. So going back to our Angelina example, we can think about Angelina doing a dance. She's performing a ballet. So she can't remember everything about all different kinds of dances. She knows that this is a ballet dance, so she's referencing in her mind ballet positions, turns, and moves as she performs. However, she doesn't need to know anything about tap and jazz, so those aren't referenced at all, and they can be collected so she can focus on the ballet moves that she needs to. There's no overhead every time an action or a mutation happens, like in reference counting, but the deallocation of memory is delayed, which means that the application needs to pause to stop the world for a longer period of time when garbage collection and deallocation of memory does happen. So Ruby uses mark and sweep garbage collection and production, sort of. In reality, most garbage collectors used in production are a mix of different garbage collection algorithms and optimizations. So Ruby actually uses mark and sweep with generational and incremental garbage collection, which incorporates pieces of reference counting type functionality into the process as well. So now we're going to jump into generational garbage collection. Once you've completed the normal mark and sweep steps, the objects that remain get promoted to the next generation. So let's look at Angelina. Let's say Angelina's learning a new dance. She learns a bunch of steps. There's a turn, there's a leap, and then she wants to do some fusion tap move. As Angelina practices, she decides that she wants to cut out all of the leaps. Those leaps can be garbage collected because she's no longer using them, and therefore that tap move as well. But she wants to keep all of the pirouettes, all of the turns. So the pirouettes stick around and get promoted to the next generation, which is like version 2, and she continues to choreograph her dance. Generational garbage collection operates under the hypothesis that most objects die young. So you might try a bunch of things out, but only a few of them stick around. So here, we're continuing to choreograph our dance. We have some steps already in place, and we have some new steps. We've chosen to only connect one of these steps to the root and to the dance steps that we already have. Every time you collect the garbage, the stuff that sticks around goes into the next generation. When you do the next round of garbage collection, you don't need to revisit what's in the old generation. You can just say, okay, that's there, that's live, it's staying live, great. You only need to go through the newest generation to mark and sweep from there. So in this generation, this node and this node would be marked, but we don't have to look at the others because they're already in the older generation. This saves time because you're not looking at every node every single time. You're simply looking at the nodes that are in the newest generation. A possible side effect of this, however, is if you have a node in an older generation and a new object gets allocated from an object in the old generation into the newer generation, because we don't check anything in the older generation, the new node will be assumed to be garbage and will be freed because that reference isn't checked. So this leap that we've added into our routine won't be remembered because it's a reference from an old object. In order to make sure that that new object is discovered, we need to put a write barrier in place. A write barrier makes sure that that reference goes into the remembered set. Through barriers, the mutator can inform the collector of what's happening. So it's basically saying like, hey, make sure to look at me, even though I'm in the old generation and you wouldn't think to do so. When a garbage collector does its thing, it'll look at everything in the new generation plus everything in the remembered set. One other aspect is that while generational garbage collection reduces the average pause time because you're not traversing the whole object graph, it does introduce some sort of permutation overhead, which pulls in some of those aspects of reference counting that we mentioned earlier. Finally, there's incremental garbage collection. So generational garbage collection optimizes mark and sweep, and incremental garbage collection optimizes generational garbage collection. Incremental garbage collection happens through the tricolor marking algorithm. The tricolor marking algorithm says that objects are white, black, or gray. When they're white, they'll be collected. When they're gray, they're referenced from the root, but we haven't looked at anything that they reference. And when they're black, they have no references pointing to anything, but they're referenced from the root. So you look at gray objects referenced from the root. You make them black. You change the colors of anything that those new black nodes reference and make those gray. Then for any gray objects, you mark them, and you take away any newly gray objects and make those black. There are none here, so you can sweep away the white objects. In more complex systems, you do this process until you sweep away the white objects. And once an object is black, you're no longer looking at what it references. The benefit of this is that you can stop it at any time. You can do a little bit at a time. You don't have to completely stop the world for a long period of time to do everything related to garbage collection all at once. You can stop, do a little bit, let the program continue, etc. But here's where there's a problem. If a black object references a new white object, it could be freed because for all of the black objects, you're no longer looking at what they reference. So here again, you install a write barrier so that it goes into that remembered set and isn't forgotten about. When you're doing a dance, this is like you can't just have turn after turn, quick move after quick move. You need higher and lower places for activity in order to catch your breath and make it through the whole routine. Again, one interesting piece of Ruby is that it's not compacting, so you can't rearrange and move Ruby objects. So if you have pages with open slots or holes, it can actually prohibit how much memory or how many pages you can destroy and have memory and how much memory can be recollected. So this is like if you could never have dancers change positions in a routine. You have 5 dancers, 2 of them walk off, but you still have dancers sort of all over the place. You can't adjust the spotlight. Ideally, they would move together so that the spacing looked right, but Ruby doesn't allow us to do that. You can't free slots while a reference to it still exists, like if you're in a loop, for example. So if you're making a request and then the system is processing it, as it's processing the request, it's creating objects. You need to retain all of those objects while the request is going. If you run out of memory, garbage collection will run. But if there's still a reference to those objects, they can't be collected. And so you can't free any of that memory. So we'll get allocated memory. Rails apps are a collection of retained memory, which are things that will be held onto forever or for a while, plus allocated memory, which will go up and down. And that combination of allocated objects plus retained objects is memory usage. Once the process finishes and a response is delivered, the garbage collector will run again and free some objects. Okay, so all of that explanation helps us look at the tools that we need in order to improve how memory is being allocated, how objects are being created and then freed to allow for enough space for the process to run. I'm going to go through the tools quickly because I have like 4.5 minutes. Okay. We'll start by looking at Scout. When you start getting those web server errors, Scout is a great tool to start out with. Using Scout, you can identify what processes or which endpoints are using the most memory allocation or have the most memory bloat. This tool also clearly shows you if your memory allocation is going up or down, which makes it really easy to figure out if you're going in the right direction. You can add this tool by using it as a Heroku add-on and following the instructions, or adding the gem to the gem file and the config file to your config folder and deploying. You can go to the Scout dashboard and then go to a specific endpoint and then to transaction traces to see what you're looking for. You want to look at the endpoint and most allocations or largest memory increase in order to find the information that you're looking for. Now, Scout won't let you dive into as many specifics as some of the other tools that we're going to discuss, but it's a great dashboard to see an overall picture and determine where to start. And additionally, if you haven't done any of those active record optimizations, then this is a great place to look for those performance impacts as well. How many people here know the movie Sneakers? Oh, just a couple. That's definitely a movie that you all have to check out. It's a really great movie from the 90s. And one of the things that they say is they say that they're investigating somebody and they say that going through their garbage is the best way to get to know someone. So earlier we talked about how Ruby uses memory, filling up these pages and slots with retained objects. The garbage collection, the GC library, is going through all of the garbage in your app to really get to know it. It has a ton of tools to help you determine what's going on along the way. So for example, GC Stat has a ton of different options. One option is total freed objects. So this is useful when you know you're creating lots of objects and maybe you want to see if the objects are being released in order to make room for new objects. By running GC Stat total freed objects before and after a method, you can see how that's working or if it's even working at all. This can help determine if your garbage collection process isn't as efficient as it could be because there are objects being used that are still being referenced from somewhere and therefore aren't being garbage collected. We're going to dive into GC Stat and a little bit of all the information that it gives. So this is all of the information that you get when you run GC Stat, and I'm only going to highlight a few of these. I tried to highlight all of them and the talk was like really long. Heap allocated pages are how many pages are available for use in the heap. They might be filled, they might be empty. It's just the total number of pages. So this is like a dance routine that you're doing. You might not take up all the time, but it's how much time you have for dance moves. Heap sorted length is the actual size of the heap. So this is the total number of slots in all of the pages. Even if a page is free or used, that length still stays the same. Each Ruby heap page has 408 slots. The size of each slot is 40 bytes. So each page can hold about 16 kilobytes. If we're thinking about this in the routine that we're doing and we're trying to choreograph it, this is like how much has been choreographed so far. Heap available slots are how many total available slots there are in all of those pages. This is like the total number of dance moves that can fit into a specific dance routine. Heap live slots are how many slots are filled with live objects that can't be garbage collected. So let's say in our dance we have a prop. You can't get rid of that prop entirely until you're done with all of the dance moves that use that prop. Heap live slots would be how many dance moves use that prop. And then heap free slots are how many available slots are left to fill before running out of memory. So that's like what's left. You have a certain amount of the song where you need to use the prop, and then the rest of it is currently free, but there's still a finite amount of time before the end of the song. Heap final slots are how many slots have finalizers attached to them, but where the finalizer hasn't run yet. So finalizers are basically run once the collection has determined that it's collecting the garbage, and it runs when the garbage is collected and an object is freed or deallocated. So this means the slots are currently busy or live, but they're about to be freed. So you're in the middle of doing a sequence of turns. Once these turns are over, you don't have to do them again. You can forget about them. So this turn is one heap final slot. Total allocated objects is how many objects are there to use. So as we work on our dance, we add in turns and we may change some of the turns. This would be like how many total turns can be worked into the dance. And total freed objects are how many objects have been deallocated and therefore their memory is available again for use. So we're choreographing, we have a total of, let's say, 8 turns we can do. We decide to get rid of 2 of them. So the total freed objects is 2, and we can continue to change the steps. And this will be the total of objects that we've removed from the dance. There are a bunch more GC Stat options, but I wanted to highlight these. You can run GC Stat in Rails console or IRB, and you can look for a specific measurement by using a command like this, GC Stat count. Using this library, the GC Profilers gives you access in your code to all of the garbage collection information. So you would do something like that. And this tells you how long it took to run, how many objects were deallocated, the total size of those objects, etc. When you ask for a GC report, this is what you get back. So this is the invoke time, the use size, the total objects, and garbage GC time, which is the total amount of time it took for the garbage collector to run. In addition, there are GC environment variables that you can look at, things like heap growth factors, malloc limits, etc. So changing these is called GC tuning. For Ruby, the maintainers preset these for sort of like something generic, but if your application is doing something specific, you can look at tweaking these a little bit, and they could make a big difference. I'm not going to go into these because that's beyond the scope of this talk. Another powerful tool is the object space library. So the object space library has lots of different options as well. It goes through, you can look at like each object and it will show you the total number of objects by class that are live. You can pass in specific classes and it'll tell you information about that specific class. It's basically, object space is like the heap, so it's basically a way of keeping track of all references to all live Ruby objects. Okay, I'm going to skip that example. This is just like the output that you get if you're looking at specific classes. Finally, you can't fix anything until you measure it, which was said at RailsConf this past year. And so the benchmarking library is really helpful for this. You can do benchmarking, which reports CPU time, system CPU time, and total real time it took to complete. This is a brief example, like our Angelina turning example. You want to see how long a process, if you just want to see how long a process took to run, this is really helpful, especially when you're looking at memory from maybe a bunch of different aspects. In Rails, these are 4 gems that I wanted to talk about, but since I'm like already out of time, I definitely didn't have enough time to talk about these, but check them out. And there's a lot here that I didn't go into. Garbage collection is actually a much more complex topic, and it differs based on what programming language you're working in. So there are also a lot of other aspects of memory, including database optimizations and other components that we didn't talk about today. Here are some resources that I used for putting together this talk, as well as some additional ones to dive into. I will post these slides within a couple of days, so these will be available. I wanted to say a really quick thank you to a couple of people who helped me through this talk. Mike Bernstein, Chris Sexton, Steve Reichert, and Jason Roloffs for fact-checking, helping with extra explanations, and being really great people to chat about throughout putting this talk together. And thank you all. I'm obviously not going to take questions because we're at lunchtime, but feel free to find me throughout the conference. I'm happy to chat about this, answer any questions, show you some slides that I had to rush through, etc. Thank you.